Our galaxy is filled with strange worlds. That might sound like an obvious statement, but the reality is far stranger than most people realize. We tend to think of our own solar system as a fair representation of what's out there. Rocky planets, gas giants, icy moons, worlds with rings, worlds with global storms. But our solar system is actually the boring neighborhood. It's the quiet suburb of the galaxy. Step just a little further out, and you start finding places that defy everything we thought we knew about planets. As of today, NASA has confirmed over 6,000 exoplanets in the Milky Way, and that number grows every week. Most of them are fairly normal, gas giants close to their stars, super-Earths, mini-Neptunes, the usual suspects. But then there are the outliers. Worlds with skies lit by multiple suns, worlds where it rains molten iron, worlds with ring systems so vast they dwarf Saturn, worlds that are hotter than many stars, worlds with no star at all. So, what are the strangest planets we have ever found? And what do they tell us about the possibilities that might still be lurking out there, waiting to be discovered? Let's find out. Let's start with something fundamental, something we take for granted here on Earth: the length of a year. We measure our lives by the annual trip around the Sun, 365 days. That feels natural to us. But in the galaxy, years come in all durations, from impossibly short to almost unimaginably long. In our own solar system, Mercury has the shortest year, just 88 Earth days. And here's a weird little fact about Mercury. Because of the way it rotates, one Mercurian day is actually twice as long as its year. That means if you lived on Mercury, you would experience 2 full orbits of the Sun in a single sunrise-to-sunrise cycle. It messes with your perception of time completely. But compared to what's out there, Mercury's year is positively leisurely. Most exoplanets we have discovered have extremely short years, and that's partly a quirk of how we find them. The transit method, which has discovered the majority of exoplanets, looks for the tiny dips in a star's brightness when a planet passes in front of it. To confirm a planet, you need to see that dip repeat at regular intervals. If a planet takes 2 Earth years to orbit its star, you have to watch that star patiently for many years before you can be sure. But if a planet orbits its star every few days, you can confirm it in a matter of weeks. That creates a strong observational bias. Most of the exoplanets we know about have years that last only a handful of Earth days. The famous TRAPPIST-1 system is a perfect example. All 7 of its Earth-sized planets orbit their ultra-cool dwarf star within a period of less than 1 month. The innermost planet, TRAPPIST-1b, completes a full orbit in just 1.5 days. But even that is not the record holder. There is a pulsar out there, a rapidly spinning neutron star that hosts a planetary mass object in an orbit that takes only 48 minutes and 58.5 seconds. Let that sink in. A full year on that world is less than an hour of Earth time. How is that possible? Pulsars are the collapsed cores of massive stars that went supernova. They are incredibly dense, packing more mass than our Sun into a sphere only about 30 kilometers across. Their gravity is so intense that it bends light around them. An object can orbit a neutron star at extremely close range, moving at a substantial fraction of the speed of light, and still maintain a stable path. But you might argue that a pulsar isn't really a star, it's a stellar remnant. So, what about a main sequence star? A star that is still actively fusing hydrogen in its core? The shortest year for a planet orbiting a main sequence star belongs to K2-137b. This Earth-sized exoplanet completes one orbit every 4.31 hours. That is not a typo. 4 hours and 18 minutes. It is orbiting so close to its star that it is practically skimming the stellar atmosphere. It is almost certainly doomed. Atmospheric drag and tidal forces will eventually tear it apart or send it spiraling into the star entirely. It's a world living on borrowed time. At the opposite extreme, we have planets with years that last so long they almost defy comprehension. There is a Jupiter mass object, beautifully named, whose orbital period is estimated at roughly 1 million Earth years. 1 million years to go around its star once. If you were born on that planet and lived a full human lifespan, you would not complete a single degree of your orbit. You would never see the seasons change. The star would appear as an almost fixed point of light in the sky, moving so slowly that it would take generations to notice any shift. Some planets, however, don't have a year at all, because they don't orbit a single star. They orbit 2 or 3 or even more. And that brings us to one of the most fascinating questions in exoplanet science. Can planets exist in multi-star systems? And if so, what are they like? The answer is yes, and they are some of the most visually spectacular worlds imaginable. Multi-star systems are far more common than you might think. If you look up at a clear night sky, many of the brightest stars you see are actually binaries. Sirius, the brightest star in the night sky, is a binary system. Alpha Centauri, our closest stellar neighbor, is a triple system. Polaris, the North Star, is also a binary. For a long time, astronomers actually thought that our single-star system might be the exception rather than the rule. But as our surveys have improved, we have learned that the majority of stars in the galaxy are actually solitary. It turns out that binary and multi-star systems are more common among massive stars, the blue and white giants, while the vast majority of red dwarfs, which make up about 85% of all stars, tend to be alone. But still, there are plenty of multi-star systems out there, and they can be incredibly complex. To understand how planets fit into these systems, you first need to understand how the stars themselves stay stable. The key concept is hierarchical organization. In a stable multi-star system, the stars are arranged in nested pairs. 2 stars orbit each other in a close binary. Then a third star orbits that binary at a much greater distance. Then a fourth star might orbit that triple system, and so on. This prevents chaotic gravitational interactions that would otherwise fling stars out of the system entirely. In a 3-star system, you have 2 stars locked in a tight binary, acting almost as a single gravitational unit, with the third star orbiting around both of them. In a 4-star system, you might have 2 binaries orbiting each other, or a binary with a single star, and then that trio being orbited by a 4th star. You can keep adding stars in this hierarchical fashion, but systems with more than 7 stars are exceptionally rare because they become dynamically unstable over long time scales. Now, add planets into that mix. The possibilities are dizzying. A planet could orbit just 1 star in the system, experiencing a sky with a single bright sun and a few distant faint companions. Or a planet could orbit the inner binary, meaning it would see 2 suns in its sky, locked in a close dance with each other. Or a planet could orbit the entire triple or quadruple system, at a vast distance. In a seven-star system, hypothetically, a planet orbiting far out would have 7 suns in its sky. But here's the catch. From that great distance, all those stars would appear as nothing more than bright points of light. They would provide very little warmth or illumination. The planet would be cold and dark, despite technically having 7 suns. If you want the dramatic view, you need to get closer. Imagine a planet orbiting a close binary pair of stars. Those 2 stars would loom large in the sky, perhaps even appearing to touch each other, and they would dramatically affect the planet's day-night cycle, its seasons, and its climate. The first confirmed planet orbiting 2 stars was discovered by the Kepler Space Telescope in 2011. It was named Kepler 16b, and it immediately earned the nickname the Tatooine Planet. But unlike the fictional desert world of Star Wars, Kepler 16b is a cold gas giant, about a third the mass of Saturn. It orbits its 2 parent stars every 229 days, and from its surface, the 2 suns would rise and set together, sometimes eclipsing each other in a spectacular celestial ballet. Since then, several more circumbinary planets have been discovered, proving that these worlds are not just science fiction, they are real. But what would it actually be like to live on a world with 2 suns? Would it be a paradise or a nightmare? Let's run a thought experiment. Imagine we take our Earth and we add a second star to the solar system. We'll keep our sun exactly as it is, and we'll place a red dwarf in a close orbit around it. A red dwarf is the smallest and dimmest type of star, as little as 7.5% the mass of our sun. Even so, the impact on Earth would be catastrophic in many ways. First, the orbit of Earth would have to change. With twice the combined mass in the center of the system, Earth's orbital velocity would need to increase to stay in a stable orbit. If we kept Earth at 1 astronomical unit from the system's center of mass, our year would become shorter. The gravitational pull from the second star would also introduce huge variations in our orbit over time. The seasons would become chaotic. The tilt of our axis would become secondary to the changing distance between Earth and the 2 stars. When the red dwarf is on the same side of the Sun as Earth in its orbit, and it happens to be winter in the northern hemisphere, you would get brutally cold conditions. When summer coincides with the red dwarf passing close, you would get scorching heat waves, the likes of which Earth has never seen. And red dwarfs are known for producing enormous stellar flares, far more powerful than anything our sun produces. These flares would regularly knock out satellites, disrupt power grids, and create planet-wide auroras that would be beautiful but deadly to our electronics. Even with the smallest possible companion star, life on Earth would be a constant struggle. Now imagine upgrading that companion to a massive blue supergiant, a star millions of times more luminous than our sun. There would be no place in the entire solar system where life could survive. The radiation, the stellar winds, the sheer heat would strip away any atmosphere and boil away any oceans. But there is one scenario where a binary system could be habitable. Binary stars can orbit each other at enormous distances, sometimes thousands of astronomical units apart, taking tens of thousands of years to complete one orbit. In such a wide binary, each star can have its own planetary system, essentially independent of the other. Earth could orbit one star normally, and the second star would simply appear as an exceptionally bright object in the night sky. It might not have a huge impact on the climate, but there is still a major problem. Massive stars like supergiants are short-lived. They are ticking time bombs. A supernova going off within 50 light-years would be catastrophic, sterilizing the surface of any nearby planet. And a supergiant in such a wide binary is still much closer than 50 light-years. So, the habitable window would be extremely narrow, both in time and in orbital configuration. It's a sobering reminder that multi-star systems, while beautiful to imagine, are often hostile to life as we know it. From planets with too many suns, let's move to planets with no sun at all. Rogue planets are one of the most mysterious and intriguing classes of objects in the galaxy. They are planetary mass bodies that are not gravitationally bound to any star. They drift through the interstellar void, completely alone, lit only by the faint glow of distant galaxies and the occasional stray photon from passing stars. We don't know exactly how many rogue planets exist. Estimates range from billions to trillions in our galaxy alone. They are essentially invisible to most of our detection methods. They don't emit their own light, and they don't orbit a star to cause a transit or a radial velocity wobble. So, how do we even know they exist? The answer is a technique called gravitational microlensing. This is one of the most elegant and powerful methods in the astronomer's toolkit. It relies on a prediction made by Einstein in 1936. According to general relativity, massive objects warp the fabric of space-time around them. Light traveling through that warped space follows a curved path. When a massive object, like a star or a planet, passes almost directly in front of a more distant star from our perspective, the gravity of the foreground object acts like a lens. It bends and focuses the light from the background star, making it appear temporarily brighter. The magnification can be substantial. Astronomers can measure this brightening event and, from its duration and shape, infer the mass of the foreground object. The key insight is that the foreground object does not need to be a star. It can be a planet, a rogue planet with no star at all. When a rogue planet drifts across the line of sight to a distant star, it creates a brief microlensing event, a tiny blip in the star's brightness that lasts a few hours or days. This is how we have detected most of our rogue planet candidates. Currently, several ground-based surveys are hunting for these events, including OGLE, MOA, and SuperMACO. They have found over 20 rogue planet candidates so far. One of the most exciting is OGLE 2012 BLG 123. If confirmed, it would be the smallest rogue planet ever discovered, with a mass roughly equal to Earth. How an Earth mass object ends up drifting alone through the galaxy is still an open question. It might have been ejected from a young planetary system during its chaotic formation. It might have formed as a protostar that failed to gather enough mass to ignite fusion, essentially a sub-brown dwarf. Or it could be something else entirely. What could conditions be like on a rogue planet? The first thing that comes to mind is darkness. Without a nearby star, the surface would be pitch black. You would not be able to see your hand in front of your face without artificial light. The only illumination would come from the faint glow of the Milky Way and perhaps occasional distant supernovae. But darkness does not necessarily mean cold. And this is where rogue planets become truly fascinating. In 1999, a research paper proposed that a rogue planet with a thick, hydrogen-rich atmosphere could retain enough internal heat to maintain liquid water oceans. The planet's core, still hot from radioactive decay and residual formation heat, would warm the interior. The thick atmosphere would act as an incredibly efficient blanket, trapping that heat and preventing it from radiating into space. In theory, such a planet could have liquid water oceans beneath a thick, dark hydrogen atmosphere. Life on such a world would be radically different from anything on Earth. Without sunlight, photosynthesis would be impossible. Any organisms would have to rely on chemosynthesis, drawing energy from chemical reactions in the planet's crust, similar to the tube worms and bacteria found around hydrothermal vents on Earth's ocean floor. It would be a world without day or night, without seasons, without a sky full of stars, just an eternal deep ocean under a heavy, dark sky. Whether such life could develop intelligence or even complex multicellularity is an open question. But the possibility alone is enough to make rogue planets one of the most compelling targets for future study. The Nancy Grace Roman Space Telescope, set to launch no later than 2027, will revolutionize our understanding of rogue planets. It has a field of view 100 times larger than Hubble, and it will conduct a dedicated microlensing survey toward the center of our galaxy, where the density of stars is highest. It is expected to discover thousands of exoplanets, including many rogue planets and free-floating Earth mass objects. We are on the verge of a revolution in our understanding of these invisible wanderers. Let's move now from the dark and cold to the extreme opposite. Let's talk about planets that are so hot they break the laws of chemistry as we know them. WASP 76b was discovered in 2013 as part of the wide-angle search for planets. It is a gas giant with a mass about 0.92 times that of Jupiter, but its radius is nearly twice as large, making it a puffy, low-density world. It orbits its star every 1.8 Earth days, placing it incredibly close to the stellar surface. This proximity has a dramatic effect. WASP 76b is tidally locked, meaning the same hemisphere always faces the star. The day side of the planet reaches temperatures of about 2,400 degrees Celsius. The night side is cooler, but still scorching, at around 1,500 degrees Celsius. At these temperatures, metals that are solid on Earth become vaporized. Iron, for example, turns into a gas. And this is where things get truly bizarre. In 2020, astronomers using the espresso instrument on the European Southern Observatory's Very Large Telescope made a remarkable discovery. They detected iron vapor in the atmosphere of WASP 76b, but only on the day side. The iron is vaporized on the blistering day side, and then powerful winds carry it toward the terminator, the boundary between day and night. As the iron reaches the cooler night side, it condenses into liquid droplets and falls as rain. Iron rain, molten metal falling from the sky. This is not a metaphor, it is a literal weather phenomenon. The detection showed that on the morning side of the planet, the iron signature was absent, consistent with it having rained out. It is the first time that weather-driven chemical variations have been detected on an exoplanet. WASP 76b is an ultra-hot Jupiter, and it likely will not be the last world we find with metallic precipitation. But as extreme as WASP 76b is, it is not the hottest exoplanet we have found. That title belongs to Kelt 9b. Kelt 9 is a star that is mercilessly hot. It has a surface temperature of nearly 10,000 degrees Celsius, almost twice as hot as our Sun. Orbiting just 5 million kilometers from this stellar inferno is Kelti 9b, a gas giant nearly twice the size of Jupiter and 3 times its mass. The dayside temperature of Kelti 9b has been measured at 4,300 degrees Celsius. That is hotter than the surface of many stars. To put that in perspective, the coolest red dwarf stars have surface temperatures around 2,500 to 3,000 degrees Celsius. Kelti 9b is hotter than that. It is a planet that is literally hotter than a star. At these temperatures, molecules cannot form. The atmosphere is a soup of individual atoms, and even some of those are being stripped away. Hydrogen atoms are boiling off the planet's surface, dragged along by the star's intense radiation and gravity at a rate of about 100,000 tons per second. Kelti 9b is actively being evaporated. In a few 100 million years, when the star Kelti 9 expands into a red giant, the planet will be completely engulfed and consumed. For now, it exists in a state of extreme agony, a world being torn apart by the very star that gives it light. Kelti 9b raises an interesting question about the definition of a planet. If a planet is hotter than a red dwarf star, does it still fit our classification? It does, because it lacks the mass to sustain nuclear fusion in its core. But it blurs the line between star and planet in a way that is deeply unsettling. This brings us to the concept of an iron gas giant. This is a theoretical class of exoplanet that might be common in the universe, but we have only begun to understand. An iron gas giant would be a planet with a core that is disproportionately rich in iron, much more so than Jupiter or Saturn. In our own solar system, the gas giants have cores that are thought to be composed of rock, ice, and metal, but the iron content is not extreme. In some exoplanetary systems, however, the available building materials might be different. If a star system formed from a molecular cloud that was particularly rich in heavy elements, the planets that formed there could have cores with a much higher iron fraction. Such a planet would be denser than a typical gas giant. It would also have a very different internal structure, with a massive solid iron core surrounded by a thick envelope of hydrogen and helium. We have not conclusively identified an iron gas giant yet, but we have found candidates. Some of the ultra-dense exoplanets that are larger than Earth but smaller than Neptune, often called super-Earths or mini-Neptunes, might actually be iron-rich worlds stripped of their atmospheres. There is also the possibility of a planet that is composed almost entirely of iron, a stripped planetary core left over from a cataclysmic collision or the evaporation of a gas giant. These worlds would have bizarre surface properties. They would be incredibly dense, with gravity several times that of Earth. They would likely have magnetic fields far stronger than Earth's, generated by the rotating iron core. They might have volcanic activity driven by radioactive decay, but no plate tectonics in the traditional sense. But the most immediate question is, can planets actually be larger than the stars they orbit? It sounds absurd, but it is a question that has a real answer. Stars, by definition, must be massive enough to sustain hydrogen fusion. That threshold is about 0.08 solar masses, or about 80 times the mass of Jupiter. Below that, you get brown dwarfs, failed stars that never ignited. Planets are below the brown dwarf threshold, about 13 Jupiter masses at the upper end. So, the smallest possible star is about 80 Jupiter masses. The largest possible planet is about 13 Jupiter masses. That means stars are always more massive than planets. But mass is not the same as volume. Some of the smallest stars, the smallest red dwarfs, and the various types of stellar remnants are incredibly compact. A white dwarf, for example, has a mass comparable to the Sun, but a radius roughly the size of Earth. A neutron star is even smaller, only about 30 kilometers across. Planets can easily be larger in diameter than these objects. In 2020, a planet named WD 1856b was confirmed orbiting a white dwarf. The white dwarf is about the size of Earth. The planet is a gas giant roughly the size of Jupiter, so the planet is vastly larger than its parent star. Imagine that. A star, the remnant of a once glorious sun, now a dim, Earth-sized ember, orbited by a planet more than 10 times its diameter. It is a stark reversal of the familiar cosmic hierarchy, and it tells us something profound about the violent history of the universe. WD 1856b must have survived the star's red giant phase, which would have expanded to engulf the planet's current orbit. That means the planet either formed elsewhere and migrated inward after the red giant phase, or it was scattered into its current orbit by gravitational interactions with other planets. Either scenario points to a dynamic and chaotic past. As for planets larger than main sequence stars, that is a trickier question. Main sequence stars range from tiny red dwarfs, about 70,000 kilometers in radius, to enormous blue supergiants millions of kilometers across. The largest known exoplanets have radii around 3 times that of Jupiter, which is about 210,000 kilometers. So, a large planet could potentially be bigger than a small red dwarf. The candidate VHS 1256-1257b is a compelling example. It was directly imaged, a rare feat, and its host star is a dim red dwarf. The planet's radius is uncertain, but it could be larger than the star. The margins of error, however, make it difficult to be certain. Both objects could be brown dwarfs, so we cannot definitively say it is a planet larger than its star, but statistically, it almost certainly exists. There must be cases out there where a giant planet, puffed up by internal heat, has a larger diameter than its diminutive red dwarf host. It is only a matter of time before we find one. Finally, let's talk about the most visually stunning exoplanet candidate we have ever encountered, J1407b. This object was first noticed in 2012, when astronomers analyzing data from the SuperWASP survey noticed something extraordinary. A star, designated J1407, experienced a series of complex deep eclipses. The star dimmed by as much as 95% at one point. That is not a typical planetary transit. A Jupiter-sized planet blocks about 1% of a Sun-like star's light. To block 95%, something enormous must be passing in front. The interpretation was that J1407b is a giant planet, or possibly a brown dwarf, surrounded by an enormous ring system. The rings were estimated to cover an area 40,000 times larger than Saturn's rings. In terms of sheer scale, the rings of J1407b would extend out to the orbit of Venus in our own solar system. The structure of the rings, as inferred from the light curve, showed multiple gaps, likely cleared by exomoons in the process of formation. It was a system that looked like a young Saturn, but on a colossal scale. The visual would be breathtaking. From the surface of a hypothetical moon within those rings, the sky would be filled with a vast, glowing arc of ring material. The parent star would be partially obscured by the ring plane. It would be a view unlike anything in our solar system. But there is a significant caveat. The original observation of the J1407 eclipse was a one-time event. The planet was predicted to have an orbital period of about 10 years, but in the years since the initial detection, no repeated eclipses have been observed. This has led to significant skepticism in the scientific community. The current scientific consensus is that J1407b is not a stable planet with a long-lived ring system. The simplest explanation is that the object was a free-floating brown dwarf or a rogue planet with its own circumstellar disk or ring system, and it just happened to pass in front of the star J1407 by pure chance. A near miss, a 1 in a million alignment, rather than a permanent member of that star system. It is also possible that the rings themselves were a transient feature, a debris disk that has since dissipated, or that the interpretation of the light curve was overly optimistic, and the object is something else entirely. As of today, J1407b remains an unconfirmed candidate. Its spectacular rings are not a certainty. They are a possibility, a tantalizing hint of what might exist, but they require more data to be taken seriously. For now, the most awe-inspiring ring system in the galaxy remains Saturn's. But the fact that we even have a candidate, a data point suggesting that such structures can exist, is a testament to the sheer variety of the universe. So, where does this leave us? We have explored planets with years that last less than an hour and years that last 1,000,000 years. We have imagined skies with 2 suns, 3 suns, or 7 dim points of light. We have considered the cold, dark oceans of rogue planets where life might flourish in the absence of any star. We have seen worlds where iron falls from the sky like rain, and worlds so hot they outshine red dwarf stars. We have contemplated planets larger than their parent stars, and ring systems that could swallow entire planetary systems. The galaxy is not just a collection of planets, it is a laboratory of extremes, and every new discovery pushes the boundaries of what we think is possible. The most bizarre exoplanets we have found so far are almost certainly not the strangest ones out there. The strangest ones are still waiting to be discovered. With telescopes like the James Webb Space Telescope and the Nancy Grace Roman Space Telescope on the horizon, we are about to enter a new era of discovery. We are going to find worlds that challenge our definitions of what a planet is, what a star is, and where the boundary between them lies. We are going to find worlds that are utterly alien, and yet somehow they will be real. That is the thrill of exoplanet science. It is not just about finding another Earth. It is about finding the impossible, and then proving it is possible after all. And that, perhaps, is the most profound lesson of all. The universe is not a static catalog of known objects. It is a dynamic, evolving canvas where the strangest discoveries are often the ones that force us to rewrite our textbooks. The exoplanets we have found, from iron rain worlds to evaporating infernos, from rogue drifters to ring giants, are not mere curiosities. They are signposts pointing to deeper truths about how planets form, how stars live and die, and how life might adapt to conditions we once thought impossible. Every new data point from the JWST, every micro-lensing event caught by the Roman Space Telescope, every subtle dip in a star's light curve, has the potential to reveal a new category of world. So the next time you look up at the night sky, remember, the most bizarre exoplanets are not behind us. They are ahead of us, waiting to be described, waiting to be named, waiting to remind us that reality is always stranger than fiction. Look up at the night sky. On a perfectly clear night, far from the glow of any city, you can see perhaps a few thousand stars. That's a humbling number, but it is a lie by omission, because around almost every single one of those pinpricks of light, there are worlds, planets. Some are rocky, some are gaseous, some are frozen wastelands. We will never visit most of them. We will never fully understand the conditions that reign on their surfaces. But some of them are so extreme, so violent, so fundamentally wrong by every instinct we have about what a world should be, that when astronomers first detected them, they assumed their instruments were broken. Tonight, we are going to visit 10 of those worlds, a planet being devoured alive by its own star, a world so dark that it makes coal look like a mirror, a planet with rings so enormous they would swallow the entire orbit of Venus around our sun, and a world where the sky rains molten rock. These are not science fiction. These are real, confirmed by NASA and the world's leading observatories. They are out there, right now, turning in the darkness. Let's begin with a planet that is, by any reasonable measure, already dead. It just hasn't finished dying yet. 1,400 light-years from Earth, in the constellation Auriga, there is a world called WASP 12b. Astronomers classify it as a hot Jupiter, a gas giant that has migrated dangerously close to its host star. But where most hot Jupiters manage to hold themselves together in that hostile proximity, WASP 12b has crossed a line from which there is no return. It orbits its star so closely that a single year on this planet lasts just 1.1 Earth days. Think about that for a moment. The planet completes an entire orbit around its sun in just over 24 hours. At that distance, the star's gravitational pull is not just warming the planet, it is physically deforming it. The tidal forces acting on WASP 12b are so extreme that the planet has been pulled out of its natural spherical shape. It is no longer a globe. It has been stretched and compressed into the shape of an egg, bulging violently toward its star on one side, elongated on the other. No planet in our solar system, not even the most extreme, experiences anything close to this level of tidal stress. And it gets worse, because the star isn't just reshaping the planet, it's eating it. Material from WASP 12b's upper atmosphere is continuously being stripped away by the star's gravity and radiation, flowing from the planet to the star in a stream of superheated gas. Astronomers have observed this directly. They have watched as the planet slowly bleeds into space. It loses the equivalent of several times Earth's mass every million years. In about 10 million years, WASP 12b will be gone entirely, consumed, erased. What makes this world so unsettling isn't just the violence of what is happening to it. It is the fact that it was once, in all likelihood, a perfectly ordinary gas giant in a stable orbit. Something disturbed that orbit. It spiraled inward, crossed the threshold from which there is no return, and is now locked in a slow, inevitable execution. A planet with no way out. Now, there is a rule in astronomy, a hierarchy of heat that feels intuitive and fundamental. Stars are hot, planets are cold by comparison, Our sun burns at around 5,500 degrees Celsius at its surface. A planet orbiting at a safe distance absorbs some of that heat and radiates the rest away. Even the hottest planets we know of should sit well below stellar temperatures. Kelty 9b breaks that rule completely. Located 670 light-years from Earth, Kelty 9b is a gas giant with a surface temperature on its day side of over 4,300 degrees Celsius. That is hotter than approximately 80% of all known stars in the Milky Way. It is a planet that is hotter than stars. Its host star, Kelty 9, is itself an unusually hot and young blue-white star, one of the most energetic stellar environments a planet could find itself orbiting. Kelty 9b orbits it in just 1.5 days, tidally locked, with the same face always pointing toward the star, absorbing a constant and relentless flood of ultraviolet and X-ray radiation. At 4,300 degrees, something happens to matter that doesn't happen anywhere else in a planetary atmosphere. Molecules cannot survive, not just complex molecules, all molecules. The heat on Kelty 9b's day side is sufficient to break the chemical bonds between atoms, tearing apart water molecules, carbon dioxide molecules, even hydrogen gas. It reduces everything to a plasma of individual atoms with no structure left, no compounds, no chemistry, just raw atomic matter, stripped and ionized. This is the critical distinction when we talk about its atmosphere. On Earth, an atmosphere is a blanket of molecular gas. On Kelty 9b, that blanket is gone. The envelope of material that surrounds the planet is a roiling sea of dissociated particles, a stellar-like plasma. It is an atmosphere only in the sense that it is gas surrounding a planet, but it is an atmosphere that has been boiled down to its most basic components, a chemical soup where no stable molecule can exist for more than an instant. You would not be burned on Kelty 9b. Burning requires molecules to combust. There are no molecules on the day side. You would be dissociated, reduced to your component atoms, before you registered anything happening at all. The planet is also slowly being destroyed. The radiation from Kelty 9 is gradually stripping this material away, layer by layer. In a few 100 million years, what is left may be nothing but a bare, exposed planetary core, a cinder at the edge of a star, the remnant of something that was once a world. But let's move from a world of pure heat to a world of pure deception. From a distance, HD 199733b is beautiful. A deep, vivid cobalt blue, strikingly similar to Earth's color from space. The kind of blue that suggests oceans, atmosphere, life. If you were looking at this planet through a telescope without knowing anything else about it, your first instinct might be hope. That instinct would be disastrously wrong. HD 199733b sits 64 light-years from Earth, and it is one of the most studied exoplanets we know of, precisely because of how deceptive it is. The blue is not from oceans. It comes from silicate particles, tiny fragments of glass suspended throughout the planet's atmosphere. These particles scatter blue light the same way water droplets scatter light in Earth's sky. The color is the same. The cause is entirely different and infinitely more lethal. Because those silicate particles don't just sit passively in the atmosphere, they are driven by winds. Winds on HD 11897333b reach 8,700 kilometers per hour. That is roughly 7 times the speed of sound. The fastest sustained winds ever recorded on Earth peaked at around 400 kilometers per hour. The winds here are more than 20 times that, and they carry those glass particles with them horizontally in a perpetual planetary storm that shows no signs of ever stopping. The result is a permanent sideways glass storm covering the entire planet. If you were to stand in that atmosphere, which you have no opportunity to do because the surface temperature sits at around 1,000 degrees Celsius, the glass wouldn't fall on you like rain falls on Earth. It would hit you like a sandblaster, traveling at supersonic speed from the side. The particles are small, but the velocity is everything. At those speeds, glass splinters don't dust you, they shred. The temperature differential between the day side and night side of this planet, around 260 degrees Celsius, is what drives those winds in a continuous loop that has been running for longer than Earth has existed. There is no season where it stops, no hemisphere where it calms, just glass and speed, and a planet that announced itself to the universe as something beautiful and turned out to be something that destroys everything that enters it. Now, imagine the opposite of that beautiful blue. Imagine a world that exists in a state of almost perfect optical absence. 750 light years from Earth, there is a planet that is, in a very real sense, invisible. Not invisible in the way a distant object is invisible because it is too faint. Invisible in the way a shadow is invisible. TRAS 2b absorbs almost all of the light that strikes it. Every photon of sunlight that hits this planet, 99.9% of it, simply disappears. The planet swallows it whole and gives nothing back. For context, coal, one of the darkest natural substances on Earth, reflects about 5% of the light that hits it. Black acrylic paint reflects around 4%. TRAS 2b reflects less than 1%. It is darker than anything we have a word for. NASA has called it the planet of eternal night, and that description, for once, is not hyperbole. But here is what makes this world even more disquieting. Because TRAS 2b orbits so closely to its host star, completing one full orbit every 2.5 days, it is simultaneously one of the most irradiated planets we know of. It is being bombarded constantly with enormous amounts of stellar energy. All of that energy arrives. Almost none of it leaves. The result is a world of absolute darkness that still glows. The heat from that bombardment builds to around 1,000 degrees Celsius on the daylight side, and at those temperatures, the planet emits a faint thermal glow. A deep, dim, barely perceptible red, not reflected light, emitted heat. Standing on the surface of TRAS 2b, you would be in total darkness, and yet the planet beneath your feet would be radiating a dull red warmth, like the embers of a fire long after the flames have gone cold. We still don't fully understand why TRAS 2b is so dark. The leading theories point to light-absorbing chemicals in the atmosphere, compounds of sodium, potassium, and titanium oxide, but none of the models account for quite this level of absorption. Something about this planet drinks light in a way science has not yet fully explained. It is a world that exists at the intersection of extreme heat and absolute darkness. Let's move from a world that swallows light to a world that swallows its own geology. Most of what we experience as weather on Earth comes down to one substance moving through 3 states. Water evaporates from the oceans, rises into the atmosphere, condenses into clouds, falls as rain, and flows back to the sea. The water cycle is one of the most fundamental processes on our planet. K2-141b has a version of that cycle, just not with water. This rocky super-Earth sits about 200 light-years from Earth and orbits its star at an extraordinary speed. A full year here lasts just under 7 hours. At that proximity, the star-facing side of K2-141b is locked in permanent exposure. The temperature on the day side exceeds 3,000 degrees Celsius. That is hot enough to melt any rock, any metal, any mineral that exists in the planet's crust. The entire dayside surface is covered in a global ocean of magma, hundreds of kilometers deep in places, with the rock beneath it perpetually melting and circulating. But it is the atmosphere that makes this world uniquely strange. At 3,000 degrees, rocks don't just melt, they evaporate. Sodium, silicon oxide, silicon monoxide, all of these minerals vaporize at the surface and rise into a thin, hot atmosphere of rock gas. That rock vapor is then carried by supersonic winds, winds driven by the extreme temperature difference between the 3,000-degree day side and the night side, which plunges to around 200 degrees Celsius. That rock vapor is swept across to the cold half of the planet, where it cools, condenses, and falls as rain. Rock rain, sodium and silicate pebbles falling from the sky. But this is not just a simple rain event. This is a global material cycle. Those rocks that fall on the night side don't just sit there, they flow. Some of them collect in frozen deposits on the dark, frigid surface. Some of them slowly migrate back toward the day side, driven by the planet's internal heat and the gradient of temperature. They melt into the edge of the day side magma ocean and rejoin the cycle. A planetary rock cycle operating at temperatures and velocities that make Earth's most violent geological events look calm. Standing on the night side of K2-141b, which you could not, because nothing survives either side of this world, you would watch rocks condensing out of the sky above you, falling, collecting, and then slowly drifting toward the glowing horizon of the magma ocean. A world that rains its own mountains back onto itself, continuously, forever. Every planet in our solar system formed billions of years ago. The heat of their formation, the violence of accretion, of collisions, of gravitational compression, dissipated long ago. What we orbit today are finished worlds, cooled, set. Their origins are invisible in their current appearance. GJ504b has not reached that stage yet. Located 57 light-years from Earth, this gas giant is only 160 million years old. That is younger than the dinosaurs were when they went extinct. In planetary terms, it is a newborn, and it is still glowing from the heat of its own birth. When gas giants form, they accumulate enormous amounts of gravitational potential energy as the material that becomes them collapses inward. That energy converts to heat. A newly formed Jupiter-class planet is initially hot, not from nuclear fusion, not from a star's radiation, but from the pure mechanical energy of its own creation. Over billions of years, that heat slowly radiates away into space. GJ504b hasn't had billions of years. It has had 160 million, and the heat is still there, radiating outward, giving the planet a surface temperature of around 230 degrees Celsius and giving it a color. GJ504b glows magenta, a deep, vivid pinkish purple. This color is produced not by reflected starlight, but by the planet's own thermal emission. We have actual photographs of this world. It is one of the few exoplanets to have been directly imaged. In those photographs, it appears as a small, bright, distinctly pink point of light sitting beside its host star. It is 4 times the mass of Jupiter. Its gravity at the cloud tops would be roughly 10 times what you experience standing on Earth. At that gravitational intensity, the human cardiovascular system cannot function correctly. Blood cannot be pumped to the brain against the weight pressing down on the body. But stand back from the physics for a moment and consider what this world represents. A gas giant in the process of becoming itself. Cooling, contracting, slowly dimming over millions of years as its birth heat bleeds into the void. In a billion years, it will look entirely different. Darker, colder, just another point of reflected light beside its star. Right now, we are catching it in its infancy, a moment that, in the life of a planet, is gone in a cosmic blink. Now, let's talk about a world that was, for a brief period, the most valuable object humanity had ever discovered. 41 light years from Earth, there is a planet called 55 Cancri E. When astronomers first analyzed it in 2012, the data suggested something extraordinary. The planet's mass and radius pointed to a composition unlike anything in our solar system. A world made largely of carbon, compressed under enormous internal pressure into its densest possible form. The conclusion was almost impossible to believe, and yet the numbers kept pointing to it. The interior of 55 Cancri E, scientists proposed, was made primarily of diamond, not traces of diamond, not diamond-bearing rock, a planetary interior of compressed crystalline carbon sitting beneath a thin layer of graphite crust. A diamond world twice the size of Earth, orbiting a star we can see with the naked eye on a clear night. The story has become more complicated since then. Later models suggested that the carbon-diamond interpretation may have been oversimplified. The planet's interior chemistry could involve other high-pressure mineral structures like Lonsdaleite or other exotic forms of carbon. The truth is likely somewhere between the two pictures. But what has not changed, what every model agrees on, is what the surface looks like. 55 Cancri E orbits its star in just 18 hours. It is tidally locked. One side is baking in permanent stellar exposure. The surface temperature on the day side reaches around 2,400 degrees Celsius. At those temperatures, the surface rock doesn't just melt. It becomes a global ocean of lava, deep, churning, covering the entire sun-facing hemisphere of the planet. Look up from that ocean, if anything could look up, and the sky above is not empty. The silicate rock evaporating from the lava surface rises and forms clouds. Those clouds reflect the lava's own glow back downward. The sky shimmers. Glowing silicate vapor catches the light of a star less than 2 million kilometers away, close enough that the star would fill an enormous portion of the sky. Beneath that sky, a lava ocean. Beneath that ocean, if the original models hold, the most compressed, most valuable mineral structure in the known universe. A world of extraordinary, inaccessible wealth, sitting on the doorstep of our solar system, wrapped in fire, locked in an orbit that makes it permanently, completely uninhabitable. The diamond, if it exists, is a geological ghost, a promise of immense value that can never be claimed. For most of human history, Jupiter was our reference point for large. The largest planet in our solar system, a gas giant so enormous that all the other planets combined would fit inside it with room to spare. Jupiter became the unit of measurement. Exoplanets are measured in Jupiter masses, Jupiter radii, compared always back to that familiar giant. Roxas 42. BB requires us to reconsider Jupiter entirely. Located about 460 light-years from Earth in the constellation Ophiuchus, ROXS 42. BB is one of the few exoplanets we have directly imaged. We have actual photographs of this object sitting beside its host star. From those photographs and the spectroscopic data they have generated, astronomers have estimated something that still strains comprehension. 42 BB has a radius approximately 2.5 times that of Jupiter, possibly larger depending on the model used. Its mass sits somewhere between 6 and 9 Jupiter masses. It is so large, so far outside the parameters of what we typically call a planet, that there is genuine scientific debate about whether the word planet even applies. The boundary between a very large gas giant and a brown dwarf, a failed star, sits at around 13 Jupiter masses. 42 BB sits below that threshold, but it occupies a strange and unsettling territory between the two categories. What makes its size more viscerally incomprehensible is the distance at which it orbits its host star. Roxas 42. BB sits at roughly 150 times the distance between Earth and the Sun, far, far beyond where standard planet formation models would predict a planet of this size could have formed from a protoplanetary disk. Something extraordinary happened in the formation of this system. Whether Roxas 42 BB formed the way planets form or the way stars form through direct gravitational collapse of a gas cloud remains unresolved. Jupiter, sitting in this planet's atmosphere, would be a moon. The gravity at the cloud tops of Roxas 42 BB is estimated to be somewhere between 5 and 8 times Earth's. The atmosphere extends thousands of kilometers above what would technically be considered the surface. The internal pressure at the core, if there is a discrete core at all, would be beyond any material science we understand. This is a world where the very physics of planetary structure are being tested at their outer limits. It exists. It is a planet, probably, and against it, Jupiter, the thing we once called enormous, is barely a footnote. After all of these worlds of pure extremity, it is worth pausing, because there is a planet out there that, by every measurement we have, is the closest thing to home that we have ever found. Kepler 442b orbits a star slightly cooler and smaller than our Sun, a K-type star that is quieter and more stable than our own. It sits comfortably within the habitable zone of that star, at a distance where liquid water could exist on its surface. It is a rocky planet, estimated at about 1.3 times the size of Earth. It receives about 70% of the solar energy that Earth receives, close enough that temperatures could be within a range that life as we know it might tolerate. On the Earth, Similarity Index, a scientific scale that attempts to quantify how Earth-like a planet is across multiple parameters, Kepler 442b scores 0.84 out of 1.0. That is the highest score of any confirmed exoplanet ever found. By every indirect measurement available to us, it is the most Earth-like world we have ever confirmed exists. It is 1 206 light-years away. Traveling at the speed of the fastest spacecraft humanity has ever launched, the Parker Solar Probe, which reached speeds of around 690,000 kilometers per hour, it would take approximately 1.9 million years to get there. We have no propulsion technology on any drawing board, in any laboratory, at any level of theoretical development that would reduce that journey to a human time scale. We know it exists. We cannot go there. Somewhere out there, 1,206 light-years from where you are sitting right now, there may be a sky, clouds, an ocean, the conditions for everything we consider normal, and we will likely never know. That distance is its own kind of terror. It is the most haunting fact about the search for another Earth. We can find it, but we cannot touch it. We have saved the most visually extraordinary world for last. In our solar system, Saturn's rings are considered one of the great wonders of the known universe. Spanning roughly 282,000 kilometers from edge to edge, visible from Earth with a modest telescope, they are a structure of such elegance and scale that the first astronomers to observe them through early instruments couldn't explain what they were looking at. Now, scale those rings up by a factor of 200. J1407b is a planet, or possibly a sub-brown dwarf. The science remains genuinely contested, orbiting a young sun-like star called J1407, approximately 434 light-years from Earth. In 2012, astronomers analyzing data from the SuperWASP survey noticed something unprecedented. When J1407b passed in front of its host star, it blocked 95% of the star's light. For comparison, Jupiter passing in front of a star typically blocks around 1%. Even a large gas giant barely dims a star noticeably. Working backward from that dimming, analyzing the pattern of how the light faded, held, and faded again across different wavelengths, astronomers reconstructed what was causing it. A ring system, but not a ring system like anything ever seen. A ring system spanning approximately 120 million kilometers in diameter. For reference, Venus orbits the Sun at a distance of 108 million kilometers. The rings of J1407b, if placed in our solar system, would stretch beyond Venus's orbit. Saturn, with its celebrated rings, would sit at the center of this system, and the rings would reach far, far past it in every direction. The ring system is not uniform. The data shows at least 37 distinct ring bands with gaps between them. At least one of those gaps shows signs of material clearing, the early stages of a moon forming within the rings, exactly as the moons of our solar system formed from the early solar disk. This ring system is not just enormous, it is actively evolving. It is building worlds inside itself. If J1407b orbited at Saturn's position in our solar system, and you looked up from Earth on a clear night, the rings would span an area of sky more than 10 times wider than the full moon. They would dominate the night sky. The question of whether J1407b is a confirmed planet with confirmed rings or something more ambiguous remains open. The initial transit has not repeated in the expected time frame, which has led some scientists to propose that the object may be a freely drifting sub-brown dwarf with a protoplanetary disk that happened to pass between us and the star in a cosmic coincidence. Others maintain the planetary interpretation and suggest the ring plane may be tilted in a way that prevents further detectable transits. Either way, whatever J1407b is, The ring system recorded in that 2012 data was real. Something passed between us and that star, and it carried with it a disk of material more vast than anything else we have found in the documented universe. Whether it is bound to that star or drifting freely through the galaxy, it exists somewhere in the dark, carrying its impossible rings with it. And somewhere out there, right now, those rings are turning. These are the worlds we have found so far. They are the extremes that our instruments have managed to detect, the outliers, the anomalies. They are the planets that break the rules. For every world we have looked at tonight, there are billions more. Most of them will be ordinary, uninteresting, but some of them will be stranger, more violent, more terrifying. The universe is not empty. It is not silent. It is filled with places where the laws of physics are pushed to their breaking point, where the familiar concepts of day and night, earth and sky, hot and cold, have no meaning. These places exist. They are real, and they are waiting for us to look. There is a tendency, after looking at worlds like these, to feel a creeping sense of vertigo. The universe, we realize, is not just vast. It is violent. It is indifferent. And the more we look, the more we find that the rules we thought were universal are really just local customs. Our solar system is a quiet suburb. These exoplanets are the inner cities of the cosmos, where everything is louder, faster, and more extreme. And yet, for all their terror, they are also extraordinary. They are laboratories of physics operating beyond anything we can replicate on Earth. They are reminders that the universe is still making things, still pushing boundaries, still creating worlds that defy our imagination. But let's be honest about what we are not going to do. We are not going to visit these worlds, not in our lifetimes, not in the lifetimes of our children. The distances are too great. The environments are too hostile. Even if we could somehow travel at a significant fraction of the speed of light, getting to Kelty 9b would still take centuries. And if we somehow arrived, we would find a planet where molecules are torn apart, where the very concept of a solid surface is meaningless, where the atmosphere is an envelope of plasma hotter than most stars. There is no landing, there is no exploration, there is only annihilation. The phrase envelope is important here. When astronomers describe Kelty 9b's outer layers, they often use the word envelope rather than atmosphere. That distinction matters. An atmosphere, as we know it, is a layer of gas held by gravity, composed of molecules that can survive. On Kelty 9b, the heat is so intense that the gas is not molecular. It is atomic. It is ionized. It is what astronomers call a bloated envelope, a puffed-up shell of particles that behave more like the outer layers of a star than the air we breathe. The planet is so close to its star that its envelope is constantly being replenished and stripped away in a cycle that cannot last. The envelope is not an atmosphere in the terrestrial sense. It is a temporary state of matter, a planetary gas shell that is actively bleeding into space. Calling it an atmosphere gives it a permanence it does not possess. It is more accurate to say that Kelty 9b is wearing its destruction as a coat. The same kind of clarification is needed for the so-called diamond planet. The popular headlines were irresistible. A world made of diamonds, worth an astronomical fortune. But the reality is more nuanced. The carbon-rich composition of 55 Cancri E is real. But whether that carbon has crystallized into diamond deep inside the planet remains an open question. The internal pressures are certainly high enough. Temperatures are also extreme, and in those conditions, carbon can form diamond, but it can also form graphite or other exotic carbon allotropes like lonsdaleite. The planet may have a diamond interior, or it may have a graphite-rich mantle, or it may have a layer of diamond surrounding a core of iron and carbon. The truth is that we are unlikely to ever know for certain. The planet is too close to its star, too hot, too far away. The diamond, if it exists, will remain forever buried beneath a global lava ocean, inaccessible to any probe we could design. The value of that diamond is purely theoretical. It is a thought experiment, a story we tell ourselves about what might be hidden under the fire. And then there is K2-141b, the world that rains rocks. We talked about the rock cycle, the evaporation of the crust, the supersonic winds, the condensation of silicate rain. But let's dwell on that image for a moment. Rain on Earth is water. It falls gently. It nourishes. Rain on K2-141b is liquid rock. It falls as pebbles and grains of hardened sodium and silicon monoxide. When it hits the ground, it does not splash. It clatters. The entire night side of this planet is a field of frozen rock deposits, slowly creeping toward the edge of the magma ocean. The death here is not just the impossibility of life. It is the constant, unending destruction of the planet's own surface. The crust is being recycled so rapidly that nothing can ever become stable. Every mountain is vaporized. Every valley is flooded with lava. The entire planet is in a state. Move, and what happens when they do. Because in 2023, astronomers discovered something that rewrote the rule book. A supermassive black hole racing across the cosmos at nearly 1,000 kilometers per second, leaving a trail of newborn stars in its wake. That discovery, known as RBH1, is our starting point for a journey that will take us from the chaotic collisions of galaxies to the very edge of reality itself. Let's set the stage. For decades, we've known that supermassive black holes sit at the centers of most large galaxies, including our own Milky Way. These behemoths can be millions or even billions of times the mass of our Sun. They're usually quiet, lurking in the dark, only revealing themselves when gas or stars get too close. But everything we thought about these objects, that they are stationary, permanent fixtures, was shattered when the Hubble Space Telescope spotted something bizarre. A perfectly straight line of young blue stars stretching across nearly 200,000 light-years of space. At first, astronomers thought it might be an edge-on galaxy, a thin disk seen from the side. But the stars were all the same age, all hot and blue, and the line ended in a blazing knot of gas with a distinct signature of doubly ionized oxygen. That kind of energy doesn't come from a normal galaxy. It comes from a shock, a cosmic ionic boom. The team, led by Yale astronomer Peter van Dokkum, considered other explanations. Maybe it was a jet from a nearby galaxy triggering star formation. But jets widen as they go, and this feature was narrowest at the front. The geometry was all wrong. The only thing that fit was something no one had ever photographed before, a runaway supermassive black hole. Follow-up observations with the James Webb Space Telescope confirmed the presence of a massive bow shock at the leading edge, like the shock wave in front of a supersonic jet. The gas in that shock was heated to millions of degrees, compressed, and then, as it cooled and streamed behind the moving object, it formed clumps that collapsed into stars. A black hole, usually the ultimate destroyer, was actually creating stars, millions of them, strung out like beads on an invisible thread. This runaway black hole, named RBH1, is estimated to be at least 10 million times the mass of the Sun. It's moving at about 954 kilometers per second relative to its surrounding environment. To put that in perspective, Earth orbits the Sun at about 30 kilometers per second. The typical speed of stars in a galaxy is a few hundred kilometers per second. This black hole is not just fast, it is supersonic, and not in the everyday sense. In space, supersonic means exceeding the speed of sound in the interstellar medium, which varies from about 10 to 100 kilometers per second, depending on the density and temperature of the gas. So, at nearly 1,000 kilometers per second, RBH1 is plowing through the thin, diffuse gas between galaxies at Mach 10 or more. That shock wave compresses the gas ahead, and the ram pressure strips material behind, creating that trail of star formation. But how did a supermassive black hole get kicked out of its home galaxy in the first place? The evidence points back to a rare and violent event, the head-on collision of two ring galaxies, a system astronomers call the cosmic owl. Ring galaxies make up only 0.01% of all known galaxies because they require a near-perfect bullseye impact, one galaxy passing directly through the center of another. When two of these rare objects collide, their central black holes spiral together. In RBH1's case, the two black holes merged. And when they did, the release of gravitational waves was asymmetrical. Think of it like the recoil of a gun. The gravitational waves carry away momentum, and if the merger is lopsided, if one black hole is slightly more massive, or the orbits are not perfectly symmetric, the resulting black hole gets a powerful kick in the opposite direction. That kick is strong enough to overcome the gravitational pull of the entire galaxy. The escape velocity from a typical galaxy is several hundred kilometers per second. For a dwarf galaxy like the one that hosted RBH1, it's lower, but still formidable. The kick gave this black hole a velocity far beyond what's needed to break free. It left its galaxy, then left the circumgalactic halo of gas, and now it's sailing through intergalactic space, leaving a wake of stars behind it. This is where the story gets even stranger. Those millions of newborn stars in the wake are not gravitationally bound to any galaxy. They are orphans, stars that will never know the embrace of a galactic disk or the companionship of a globular cluster. They were born in the wake of a fleeing monster, and they will drift through the void between galaxies, slowly spreading out as they follow their own orbits around the black hole, or simply go their separate ways. Their fate is a lonely one. In the far future, these stars will exhaust their nuclear fuel and die. Some will become white dwarfs, cooling over trillions of years into cold cinders. Others, the most massive, will collapse into neutron stars or even small black holes. And all of them will be isolated, with no neighbors for millions of light years. They are the permanent memory of a black hole that once passed through. But the RBH1 discovery is not just a curiosity. It forces us to rethink how common these runaway black holes might be. Galaxy mergers happen all the time. Every large galaxy has likely undergone multiple mergers over its lifetime. If each merger can produce a binary black hole, And if enough of those binaries merge with a third black hole, or with each other asymmetrically, then supermassive black holes might be ejected from their galaxies at such speeds more often than we think. The problem is, they are incredibly hard to see. A black hole itself is invisible. We only notice it when it interacts with gas and dust, or when it creates a bow shock strong enough to trigger star formation. RBH1 was only spotted because it happened to be plowing through a region dense enough to produce that spectacular trail. How many others are out there, silently racing through the emptiness, leaving no trace at all? Missions like Euclid and the Nancy Grace Roman Space Telescope, with their wide-field surveys, will scan the sky for more such streaks. Machine learning algorithms are being trained to spot these faint, linear signatures. We may go from one confirmed runaway to an entire population. Now, let's take a step back and consider the scale of black holes. RBH1 is 10 million solar masses. That's huge, but tiny compared to the giants that lurk in the centers of some galaxies. The black hole at the heart of the galaxy M87, the one famously imaged by the Event Horizon Telescope, is about 6.5 billion solar masses. Its event horizon spans about 38 billion kilometers, more than twice the diameter of Pluto's orbit. And then there's TON 618, one of the most massive black holes known, at 66 billion solar masses. Its event horizon would be about 1,300 astronomical units across, 20 times the size of our entire solar system. But even that is just a speck compared to what's theoretically possible. Black holes can, in principle, grow without limit, as long as they have a supply of matter to feed on. The only constraints are time and the availability of food. Given enough time, a supermassive black hole could grow to the size of a small galaxy. But what if a black hole could grow even larger? What if it could grow to contain everything we see? This is where the idea of being inside a black hole comes in. The Schwarzschild radius, the distance from a black hole's singularity to its event horizon, is directly proportional to its mass. A black hole, with the mass of the entire observable universe, would have a Schwarzschild radius roughly equal to the radius of the observable universe. This is not a coincidence. It's a mathematical consequence of the fact that the universe's average density is just above the critical density for a black hole. In other words, if you took all the matter and energy we can see, all the galaxies, all the dark matter, all the radiation, and compressed it into a single spherical region, that region would be dense enough to form a black hole with an event horizon that exactly matches the size of the observable universe. So, are we inside a black hole? The idea isn't new. It's been discussed since the 1970s, but it's important to clarify what this means and what it doesn't. First, let's address the terminology. The term dark star historically referred to a Newtonian object Jean-Michel and Pierre-Simon Laplace proposed in the 18th century. A star so massive that its escape velocity exceeds the speed of light. They imagined that light would be slowed by gravity and would fall back. That's not quite what a black hole is in general relativity. In Einstein's theory, gravity warps space-time itself. A black hole is a region where the curvature becomes infinite at the singularity, and the event horizon is a one-way membrane. Nothing, not even light, can escape, because all paths lead inward. There is no dark star in the Newtonian sense. That concept was a precursor, a brilliant guess that happened to get the idea right even if the physics was wrong. Today, we use black hole to describe the relativistic object. So, when we talk about the possibility of being inside a black hole, we're talking about being inside an event horizon defined by general relativity, not a Newtonian dark star. Now, back to the huge black hole idea. If the observable universe were inside a black hole, then the Big Bang would correspond to the singularity of that black hole. Our entire cosmic history, the expansion of space, the formation of galaxies, the evolution of life, would be unfolding inside the event horizon of a black hole that exists in some larger parent universe. This hypothesis naturally explains why the universe appears flat and homogeneous, because just like inside any black hole, the interior can be remarkably uniform. It also explains why the cosmic microwave background has a near-perfect black-body spectrum. It's the thermal echo of the collapse. And here's the kicker. From the outside, that black hole would look like any other. It would have a mass equal to the total energy of the universe inside it. But we would never be able to see out, because the event horizon is an absolute barrier. We are trapped, but we don't feel trapped, because from our perspective, space seems infinite. Does this mean we are inside a black hole right now? Many cosmologists are skeptical. The observed universe is not in a state of collapse. It's expanding at an accelerating rate. A black hole interior, on the other hand, is usually described as a collapsing region. But there are solutions in general relativity, like the Schwarzschild metric, that allow for a time-symmetric picture, a white hole, which is the time reverse of a black hole. Some theorists have proposed that the Big Bang could be a white hole, and we are inside a black hole that is connected to a white hole via a wormhole. It gets messy. The point is, the idea is tantalizing but far from proven. However, it highlights how our understanding of black holes has evolved. The discovery of RBH1 gives us a new way to think about black holes and their relation to the cosmos. Here is an object that was once central to its galaxy, now ejected and wandering. Its existence proves that black holes are not fixed. They can be mobile, they can leave their homes, and that means the largest black holes, the ones that might contain entire universes, could also be moving. But if we are inside a black hole, could its motion affect us? That's an open question. The interior of a black hole is causally disconnected from the outside. We would not experience any acceleration from the motion of the parent black hole because all reference frames inside are equivalent. As long as the black hole is large enough, tidal forces would be negligible. So we could be hurtling through a larger cosmos at an incredible speed, and we would never know. Let's not get too lost in speculation. The concrete, verified discovery of a runaway black hole is already astonishing enough. It teaches us about the extreme dynamics of galaxy mergers. When two galaxies collide, the supermassive black holes at their centers first form a binary system. Over millions of years, they lose orbital energy through gravitational radiation and eventually merge. If the merger is asymmetric, the recoil kick can reach thousands of kilometers per second. For a black hole to escape its host galaxy, it needs to exceed the galactic escape velocity. For a typical large galaxy like the Milky Way, escape velocity near the Sun's position is about 550 kilometers per second. For a dwarf galaxy, it's much lower, maybe 200 kilometers per second. RBH1's speed of 954 kilometers easily exceeds both. That's a kick with the energy equivalent to the explosion of millions of supernovae concentrated into a single object. Now, what about the orphan stars in the wake? As the black hole plows through the circumgalactic and intergalactic medium, the gas it shocks becomes compressed. But the black hole itself does not gravitationally capture much of this gas. Instead, the shock-heated gas streams around the black hole and forms a dense, turbulent tail. Within that tail, instabilities cause the gas to fragment into clouds, and those clouds collapse into stars. This process is remarkably efficient. The trail contains roughly 100 million solar masses of stars. That's a small galaxy's worth of new stars, all formed in the wake of a single black hole. These stars will have a peculiar velocity distribution. They are not orbiting the black hole. They are essentially left behind, moving at roughly the speed of the black hole at the time they formed. Over time, the gravitational pull of the black hole will slow it slightly, but the stars will continue on their nearly ballistic trajectories. Eventually, the black hole will outrun the densest parts of the gas, and star formation will stop. The trail will become a long, thin stream of aging stars, slowly fading and spreading. This phenomenon gives us a new way to hunt for invisible black holes. If we see a long, thin, straight stream of young stars in intergalactic space, it could indicate a hidden supermassive black hole at the head. Astronomers are already scanning the sky with automated tools to find more such features. The Vera Rubin Observatory, when it comes online, will survey the entire southern sky every few nights. It will detect countless transient events, but it will also capture thousands of faint, elongated structures. With the help of machine learning, we might find dozens of runaway black holes within the next decade. Each one will add to our understanding of galaxy evolution and black hole dynamics. But let's return to the idea of being inside a black hole. The title of this video poses a question. This black hole is so enormous that we might actually be inside it. The black hole in question could be the one that contains the entire observable universe. Our universe's critical density is about 10^29 grams per cubic centimeter. That's extremely low, but spread over a volume of 4 by 1080 cubic meters, the volume of the observable sphere. The total mass is around 10^53 kilograms. Using the Schwarzschild formula, the event horizon for that mass would be about 13.8 billion light-years in radius. Coincidentally, the same as the age of the universe times the speed of light. This numerical coincidence has led some to propose that the universe is literally a black hole. The problem is that the observed universe is not a static sphere. It's expanding. And the Schwarzschild solution describes a static, non-rotating black hole. However, there are solutions for rotating and expanding black holes, like the Kerr metric. Some cosmologists have tried to model the universe as the interior of a Kerr black hole, but these models have their own issues. Perhaps the most compelling argument against being inside a black hole is the cosmic microwave background. Inside a real black hole, you would expect the sky to be dominated by a highly anisotropic glow, not the nearly uniform 2.7 Kelvin radiation we see. But black holes are not completely isolated. They can accrete matter and emit Hawking radiation. For a black hole as large as the universe, Hawking radiation would be negligible. The temperature would be far below the cosmic microwave background. So, no contradiction there. In fact, the extreme uniformity of the CMB is a hallmark of inflation, but it could also be a natural consequence of the initial conditions inside a black hole. We are wading into deep waters. The truth is, we don't know whether we are inside a black hole. The hypothesis is not testable with current technology, but it's a beautiful thought experiment that connects the microcosm of black hole physics with the macrocosm of cosmology. And it becomes even more intriguing when we consider that black holes themselves might be universes. The interior of a black hole, according to some theoretical models, could spawn a new universe inside it. Our universe might be the interior of a black hole that formed in some parent universe, and the supermassive black holes we observe in our own universe could be seeds for baby universes, each one a potential new reality. This is not just fantasy. There are serious researchers who work on these ideas. They argue that the singularity inside a black hole might be avoided if quantum gravity effects cause a bounce, leading to an expansion that resembles our Big Bang. In that picture, every black hole could be a gateway to a new universe, and we might be living inside the aftermath of one such event. The discovery of RBH1 adds a new perspective. If black holes can be ejected from their host galaxies, then perhaps these baby universes can also be born in strange places. But again, this is highly speculative. Let's ground ourselves in what we know for certain. We know that supermassive black holes exist and they can move. We know that galaxy mergers are messy and can fling black holes away. We know that these runaway black holes can create trails of stars, giving us a way to detect them. We know that the largest black holes we've observed are in the tens of billions of solar masses, and we know that the universe is so large that it borders on the edge of black hole density. All these facts are connected. They paint a picture of a universe that is far more dynamic and interconnected than we once thought. The orphan stars left behind by RBH1 will never know the light of a parent galaxy. They will drift through the quiet void, perhaps for hundreds of trillions of years, until they finally evaporate or collapse. Their existence is a direct consequence of a black hole's journey. And perhaps we too are riding inside a black hole on an even grander journey. The Milky Way itself might be hurtling through some larger cosmic structure, and we would never feel it. As we continue to explore the cosmos with ever more powerful telescopes, we will keep finding new surprises. The runaway black hole was a surprise. The perfectly straight line of stars was a surprise. Just a few years ago, no one expected to see anything like it. That's the beauty of astronomy. Nature is always more inventive than our theories. The idea that we live inside a black hole may sound far-fetched, but so did the idea of a runaway black hole creating stars. The universe is full of possibilities, so let's keep looking. Let's keep wondering. The next discovery might be the one that finally tells us where we truly are. And whether that place is the interior of a black hole or a garden-variety universe, it will be more magnificent than we can imagine. Until then, we have the story of RBH1, a black hole on the run, leaving a path of light across the darkness. It reminds us that even the most destructive forces can give birth to new life, new stars, and new mysteries. And maybe, just maybe, that's the story of our own universe. We are the children of a black hole, born in its wake, heading toward a destiny we can only guess at. The journey is far from over. The journey is far from over. And as we stand at the precipice of this cosmic mystery, it's worth considering what it means for our place in the universe, not just as astronomers, but as conscious beings trying to make sense of it all. The runaway black hole, RBH1, is a single data point, but it is a profound one. It shows us that black holes are not static anchors. They are wanderers, capable of traversing the voids between galaxies. And if one can be kicked out, then many can. The question that follows is as staggering as it is simple. If black holes can leave their galaxies, could our own galaxy's central black hole, Sagittarius A, ever become a runaway? Could the Milky Way one day send its heart hurtling through intergalactic space? Let's examine that possibility. Sagittarius A is about 4.3 million solar masses, much smaller than the 10 million solar masses of RBH1, but still a supermassive black hole. It sits quietly at the center of our galaxy, surrounded by a dense cluster of stars. For it to be ejected, something catastrophic would have to happen. The most likely trigger would be a merger with another supermassive black hole, say from the Andromeda galaxy, when it collides with the Milky Way in about 4.5 billion years. During that merger, the two black holes would spiral together, eventually merging. If the merger is asymmetric, the resulting black hole could receive a gravitational kick. The question is, how strong would that kick be? Simulations suggest that kicks can exceed 1,000 km/h for certain configurations, but the exact velocity depends on the spin directions and mass ratios of the merging black holes. For the Milky Way-Andromeda merger, the combined black hole would be around 10 million solar masses, similar to RBH1. If the kick were strong enough, it could send the merged black hole flying out of the new galaxy. But would it escape? The escape velocity from the combined system would be higher than from a single galaxy, probably a few hundred km. A kick of 500 km might not be enough, but a kick of 1,000 km would definitely do it. So yes, it is possible that a future Milky Way could lose its black hole. And then what? The galaxy would be left without its central anchor. Stars that once orbited the black hole would be disrupted. Some would be thrown outward. Others would fall into chaotic orbits. The galaxy would slowly evolve, but without the black hole's influence, the central region might become less active. But the real loss would be invisible. The black hole's gravitational influence on the galaxy's dynamics is relatively small compared to the dark matter halo. The galaxy would survive. The black hole, however, would become a solitary traveler, perhaps accompanied by a small cluster of bound stars that were too close to escape. Those stars would be the black hole's only companions as it drifts into the void. Millions of years later, if it passed through a gas cloud, it could create its own trail of stars, just like RBH1. The Milky Way's heart, once the center of our cosmic home, would become a wanderer, leaving a luminous scar across the universe. Now, let's step back and consider the scale of these events. The phrase supersonic in a cosmic context is almost laughably inadequate. RBH1 is traveling at 954 kilometers. The speed of sound in the interstellar medium is about 10 kilometers. So RBH1 is moving at roughly 95 times the speed of sound. That's hypersonic in any earthly sense. But in space, the relevant comparison is the escape velocity from the galaxy, which we already discussed. Another way to think about it, the black hole is moving so fast that it would cross the entire diameter of the Milky Way in about 200 million years. That's a blink of an eye in cosmic time. And yet, from our perspective, It's almost stationary. We would never see it move across the sky because it's 7.7 billion light-years away. But the shock wave it creates is enormous. The bow shock alone is millions of light-years across, compressing gas and triggering star formation. The energy involved is staggering. The kinetic energy of a 10 million solar mass black hole moving at 954 km is about 10 to 52 ergs. That's equivalent to the energy output of a billion supernovae. That is the scale of the event that created the trail of stars. And yet, this is just one black hole. The universe is filled with supermassive black holes, probably hundreds of billions if we count those in every galaxy. A fraction of them have been or will be ejected. That means there could be a huge population of rogue supermassive black holes drifting through intergalactic space. Some might be accompanied by a faint glow of stars, like RBH1. Others might be truly dark and invisible, detectable only through gravitational lensing or the motion of surrounding gas. The more we look, the more we may find. The Nancy Grace Roman Space Telescope, with its wide-field survey, will cover an area of sky 100 times larger than Hubble's deepest fields. It will see billions of galaxies. Among them, automated algorithms will look for straight, thin streaks of blue light. Those streaks could be the signatures of runaway black holes. Machine learning can be trained to recognize the characteristic shape: a narrow head, a broadening tail, and a bow shock. In a few years, we might have a catalog of hundreds of such objects. Each one will tell a story of a violent galactic merger, a black hole merger, and a gravitational kick. But the most extraordinary possibility is that one of these runaway black holes might be the one that contains our own observable universe. Think about that for a moment. If the universe is inside a black hole, then that black hole is not static. It could be moving. It could have been ejected from its parent galaxy in a similar manner. Our entire cosmic history, the Big Bang, the formation of the Milky Way, the evolution of life, would be happening inside a black hole that is itself traveling through some larger cosmos. The kick that launched it might have happened billions of years ago, before our universe began. Or perhaps the kick is still happening, and we are accelerating along with it. But, as we said, we wouldn't feel it, because inside the event horizon, all reference frames are equivalent. Speed is relative. The idea boggles the mind, but it is a logical extension of the physics we already know. Now, there is a subtlety here about being inside a black hole. Many people imagine that being inside a black hole means being crushed by gravity. But that's only true if the black hole is small. For a black hole the size of the observable universe, the tidal forces are negligible. The Schwarzschild radius for the observable universe is about 13.8 billion light-years. That's exactly the radius of the observable universe. So, if we are inside a black hole, we are currently at a distance from the singularity that is far beyond the event horizon. We are in the interior, where space-time is highly curved, but not necessarily collapsing. In fact, some models suggest that the interior of a black hole can be a universe that expands forever, with the singularity replaced by a bounce. This is the black hole cosmology hypothesis. It was first proposed by Indian astrophysicist Raj Gopal in the 1970s, later refined by Nikodym Popławski at the University of New Haven. Popławski's idea is that every black hole is a gateway to a new universe. The singularity is not a point of infinite density, but a bridge to a new, expanding region. Our Big Bang is the result of such a bounce. If that's true, then the supermassive black holes we observe in our universe are the seeds of other universes. And the runaway black hole, RBH1, might be carrying a baby universe inside it, hurtling through space. It's a stunning thought. That black hole, which we see as a destructive monster, might actually be a cosmic womb. Of course, we must be careful not to overstate the evidence. The black hole cosmology is a speculative extension of general relativity and quantum gravity. It has not been tested. The observed properties of the universe, the anisotropy of the cosmic microwave background, the large-scale structure, must be consistent with such a model. So far, they are not obviously inconsistent, but they are not uniquely predicted either. The hypothesis remains on the fringe, but it is a place where science and imagination meet. What is not fringe is the reality of runaway black holes. RBH1 is real. Its trail of stars is real. The gravitational kick that propelled it is a direct consequence of general relativity. And this discovery opens a new window into the dynamics of galaxy evolution. For decades, we thought of black holes as immovable objects, anchored to the centers of galaxies. Now we know they can be kicked out like a soccer ball. And when they go, they take a part of the galaxy with them. Sometimes a trail of newborn stars that will outlive the galaxy itself. The orphan stars in that trail have a fate worth considering. They are not gravitationally bound to the black hole. They were simply born in its wake. As the black hole continues to move, it will leave them behind. They will form a long, thin stream, gradually spreading due to their own random motions. Over billions of years, the stream will widen and dissolve into the intergalactic medium. Some of these stars might eventually be captured by other galaxies. Others will drift for trillions of years, slowly dimming as they exhaust their nuclear fuel. The lowest mass stars, red dwarfs, could shine for trillions of years, outlasting the black hole's journey. In the far future, when the universe has expanded and galaxies have evaporated, the orphan stars will be among the last sources of light. They will be the ghosts of a black hole's passage, a reminder of a time when galaxies collided and black holes fled. And what of the black hole itself? RBH1 will continue its journey, perhaps forever. It may eventually encounter another galaxy, where it could sink to the center and merge with a new black hole. Or it might pass through a dense gas cloud and create another trail of stars. Or it might simply wander in the void, growing colder and quieter until the universe itself ends. Its mass will remain unchanged, barring any accretion. It will be a permanent monument to the violent merger that created it. Now, let's bring it back to you, the viewer. Why should you care about a black hole that is 7.7 billion light-years away, moving at nearly 1,000 km, creating stars in its wake? Because it changes how we think about our own existence. We live in a galaxy that will one day merge with Andromeda. That merger could produce a runaway black hole. Our own solar system might be affected. Though the chances are slim, the gravitational disruption could send stars careening through the galaxy. But more importantly, the discovery of RBH1 shows us that the universe is not static. It is a place of constant motion, of violent events, of creation and destruction intertwined. The same physics that governs the motion of planets and stars also governs the most massive objects in the cosmos. We are part of that story. We are made of elements forged in stars, and those stars were born from gas that was compressed by shock waves that might have come from black holes like RBH1. In a very real sense, the atoms in your body may have been influenced by a runaway black hole billions of years ago. The title of this video asks, "This black hole is so enormous that we might actually be inside it." We have explored the possibility that the entire observable universe is inside a black hole. That is a mind-bending idea, but it is not necessary for the wonder. The black hole that is RBH1 is enormous enough on its own. At 10 million solar masses, it is 1,000,000 times more massive than our Sun. And yet, it is a speck compared to the largest known black holes, like the one at the center of Home 15A, which is 40 billion solar masses, or TON 618, which is 66 billion solar masses. Those are truly colossal. If a black hole of that size were in our galaxy, it would distort the orbits of stars for thousands of light years. And if we were inside such a black hole, we wouldn't even know it, because the event horizon would be so vast that we would never encounter it. The density inside such a black hole is incredibly low, much lower than the density of air. The interior would be nearly empty, just like our universe. The analogy is irresistible. So, are we inside a black hole? The jury is still out, but what we do know is that black holes are everywhere. They are moving, and they are connected to the birth and death of stars. The story of RBH1 is a reminder that the universe is full of surprises. Every time we think we have understood it, it throws something new at us. That is the joy of science. And as we continue to build larger telescopes, more sensitive detectors, and more powerful computers, we will keep unveiling the hidden secrets of the cosmos. The journey is far from over. In fact, it is just beginning. The runaway black hole has left a trail of light that we can follow. And perhaps, just perhaps, that trail will lead us to the ultimate truth, that we are not just observers of the universe, we are participants, riding inside a black hole on an epic voyage through a reality that is stranger than we ever imagined. So, keep looking up. Keep asking questions. The next discovery might be the one that changes everything. There is a very real chance that the most powerful machine ever built by human hands could, at any moment, produce something that has haunted our nightmares for decades: a black hole. Not some distant, astronomical monster lurking in the heart of a galaxy, but a microscopic singularity, born right here on Earth, inside a concrete tunnel under the Swiss-French border. And if you think that sounds like the plot of a sci-fi thriller, you are not alone. When the Large Hadron Collider first powered up in 2008, headlines screamed that the end of the world was imminent. Lawsuits were filed to stop the experiment. People genuinely believed that a man-made black hole would consume the planet before they could finish their morning coffee. Of course, we are all still here. The world didn't end. But here's the twist. CERN's own documentation, even today, admits that the LHC could create a black hole. The question is not whether it's possible. The question is what would happen if it did? And the answer, as we'll see, is far stranger and far more fascinating than you might expect. Let's start with the machine itself. The Large Hadron Collider is a marvel of engineering. A 27-kilometer ring of superconducting magnets, chilled to temperatures colder than outer space, buried 100 meters underground. Inside that ring, two beams of protons are accelerated to 99.9991% the speed of light. That is so close to light speed that the protons are moving about 3 meters per second slower than the ultimate cosmic speed limit. When these beams cross, which happens 1 billion times every second, the protons slam into each other with a combined energy of 13.6 tera-electron volts. That energy is the key. According to Einstein's famous equation, energy can be converted into mass. In the extreme conditions of those collisions, heavy particles that haven't existed since the first moments after the Big Bang can be created, if only for a fleeting instant. This is how we discovered the Higgs boson. This is how we study the fundamental building blocks of matter. But energy can also, in theory, be concentrated into a tiny region of space with enough force to warp space-time into a black hole. So why would anyone worry? Because black holes, in the popular imagination, are cosmic vacuum cleaners. You get too close and you're gone, stretched, spaghettified, and erased from existence. The idea of one popping into existence in a laboratory seems like a catastrophic mistake. But the physics behind it is nuanced. To understand what would actually happen, we need to talk about the energy required to make a black hole in the first place. In our everyday universe, black holes form when massive stars collapse. You need a star at least 20 times the mass of our Sun to crush its own core into a singularity. That's an astronomical amount of matter. The LHC, on the other hand, is smashing together particles that weigh essentially nothing. How could that possibly create a black hole? The answer lies in a concept called the Planck energy. The Planck energy is a theoretical threshold, a value so enormous that classical physics breaks down, and quantum gravity must be considered. To give you a sense of scale, the Planck energy is about 1 quintillion times larger than the energy the LHC can produce. By that measure, there is no chance whatsoever that the LHC could ever create a black hole, not even close. However, and this is a big however, that calculation assumes our universe has only the 4 dimensions we are familiar with, 3 of space and 1 of time. But many theoretical physicists, especially string theorists, propose that additional spatial dimensions exist, curled up so tiny that we can't perceive them. If those extra dimensions are real, they change the rules of gravity. Instead of gravity being incredibly weak, it could become much stronger at very small scales. That would lower the Planck energy, potentially down to a level that the LHC can reach. In that scenario, a collision at 13.6 tera-electron volts might just be enough to create a microscopic black hole. Now, this is still speculative. No one has proven the existence of extra dimensions. But if they do exist, then yes, CERN could theoretically produce a black hole. And that brings us to the crucial question: what would happen next? Most people assume instant doom. The black hole would start devouring matter, growing larger, and then sink to the center of the Earth, consuming the planet from the inside out. It's a terrifying image, and it has fueled countless doomsday scenarios. But the reality is almost comically anticlimactic. In all likelihood, the black hole would evaporate practically the moment it formed. This is because of a phenomenon predicted by Stephen Hawking in 1974, known as Hawking radiation. Hawking showed that black holes are not truly black. They emit a faint glow of radiation due to quantum effects near the event horizon. This radiation carries away energy, causing the black hole to lose mass. For a large black hole, like one at the center of a galaxy, This process takes unimaginably long, trillions of years. But for a tiny black hole, the evaporation is incredibly fast. A black hole with the mass of a few protons would radiate away its energy in a fraction of a second, releasing about the same energy as a grain of sand dropping a few centimeters. If you were standing nearby, you might not even notice. The detectors at CERN are sensitive enough to spot the telltale signature of such an event, but so far, they haven't seen anything. That doesn't mean it's impossible. It could just mean that extra dimensions don't exist at the energies we've probed. But even if Hawking radiation is wrong and the black hole somehow stabilizes, the danger remains surprisingly low. Let's imagine a worst-case scenario. No Hawking radiation, extra dimensions exist, and a microscopic black hole is born. What would it do? First, it would have a tiny mass, maybe a few trillionths of a gram. That's not enough to exert any significant gravitational pull. Gravity is the weakest of the fundamental forces. A paperclip on your desk exerts more gravitational force on you than that black hole would. But wouldn't it start gobbling up nearby matter? The key is scale. A microscopic black hole's event horizon is smaller than a proton. For it to absorb anything, that particle must wander directly into that infinitesimally small region. Atoms, however, are mostly empty space. The nucleus of an atom is like a marble sitting in the middle of a sports stadium. The electrons are like tiny gnats buzzing around the stands. For our black hole to hit a nucleus, it would have to thread a needle of astronomical precision. Even if it did, the black hole would absorb that nucleus, gaining a minuscule amount of mass. But then what? Without an electric charge, the black hole would simply fall through the surrounding matter. It wouldn't be attracted to atoms because gravity is so weak, and it wouldn't be repelled by electromagnetic forces because it's neutral. So it would sink through the floor, through the rock, straight toward the center of the Earth. But it would keep going. In fact, it would pass right through the core and out the other side, oscillating back and forth like a pendulum, losing energy only through extremely rare collisions. Each collision would add a tiny bit of mass, but the probability of a collision is so low that even over billions of years, the black hole would remain microscopic. By the time the Sun becomes a red giant in 5 billion years, the black hole would still be tiny and harmless, quietly oscillating through the planet. This is where we address the idea you may have heard, that a black hole would sit harmlessly at Earth's center. Actually, that's not quite accurate for a neutral black hole. It wouldn't stop at the center. It would pass through it, like a ghost. But because of Earth's gravity, it would gradually slow down due to tidal forces and rare interactions with matter. Over a very long time, it could eventually become trapped at the center, oscillating with decreasing amplitude. But even then, it would pose no danger. Its gravitational pull would be negligible. The only way it could grow is if it somehow encountered dense matter. But the core of the Earth is already dense, but not dense enough to meaningfully increase the black hole's capture rate. You would need an object with nuclear densities, like a neutron star, for a black hole to accumulate mass quickly. Our planet is far too diffuse. So yes, a microscopic black hole could end up sitting at Earth's center. But it would be as harmless as a dust mote in a cathedral. It would not consume the planet. It would not collapse the Earth into a sphere of nothing. It would just sit there, and you would never know. This might seem anticlimactic. After all, We are talking about the possibility of creating a black hole, the most extreme object in the universe. And it turns out it would be about as dangerous as a spilled cup of coffee. But that's physics for you. The universe has a way of being far more mundane than our fears imagine. However, there is a different kind of catastrophe that is genuinely terrifying, and it's one that CERN could theoretically trigger. It's not a black hole. It's something called vacuum decay. Vacuum decay is the idea that our universe might be in a false vacuum state, a state that is stable for now, but not the lowest possible energy state. Think of it like a ball sitting in a small dip on a hillside. It's stable, but if you give it a big enough push, it could roll down into a deeper valley, releasing a massive amount of energy. That deeper valley is the true vacuum. If a region of space were to tunnel into that true vacuum, it would expand outward at the speed of light, rewriting the laws of physics as it went. Everything in its path, atoms, molecules, stars, galaxies, would be torn apart and replaced by a different set of fundamental particles. The universe as we know it would cease to exist. And here's the terrifying part. Very high-energy particle collisions, like the ones at the LHC, could theoretically catalyze that transition. The energy of the collision might be enough to nudge a tiny patch of space-time into the true vacuum, creating a bubble that expands without bound. This is not a fringe idea. It's a genuine, if extremely unlikely, possibility discussed in serious physics literature. Unlike a black hole, which would likely be harmless, vacuum decay would be instantly and utterly fatal to the entire universe. It's arguably the most catastrophic event that could ever happen. So, why aren't we more worried about vacuum decay? Because the energy required to trigger it is far, far beyond anything we can produce. The LHC operates at 13.6 TeV. The energy needed to nucleate vacuum decay is thought to be at the Planck scale, quintillions of times higher. But there is a catch. Some theories suggest that the Higgs boson itself, which the LHC discovered, could be a sign that our vacuum is metastable. In fact, measurements of the Higgs mass hint that the universe might be in a false vacuum, teetering on the edge of decay. If that's true, then a high-energy collision might, in principle, provide the necessary push. But the numbers still suggest we are safe by many orders of magnitude. Still, the fact that vacuum decay is even a mathematical possibility makes the black hole fear seem almost quaint. A black hole would be a local event. Vacuum decay would be the end of everything. And it's something that CERN, however unintentionally, is at least theoretically tinkering with. Now, you might recognize some of these ideas from popular culture. The anime and visual novel series Steins Gate famously revolves around a group of amateur scientists who accidentally create a microwave that can send messages to the past. The story's central tension comes from the fear of altering history, but the show also references real particle physics, including the Large Hadron Collider and the possibility of black hole creation. In one memorable scene, the protagonist, Okabe Rintaro, obsesses over the idea that the LHC could generate a black hole that would destroy the world. The show uses that fear as a metaphor for the unintended consequences of meddling with forces we don't fully understand. It's a brilliant narrative device because it taps into the very real anxiety that many people feel when they hear about experiments like CERN's. We worry that scientists are playing with fire and that one misstep could lead to catastrophe. While Stein's Gate is fiction, the underlying science it plays with is real. The LHC does push the boundaries of what we know, and while the specific black hole scenario in the show is dramatized, it captures the spirit of the public's imagination and our collective fascination with apocalypse. So, where does that leave us? CERN has been running the LHC at increasingly higher energies for over a decade. It has performed quadrillions of collisions. No black holes have been observed. No vacuum decay bubbles have been detected. The safety analyses that were conducted before the LHC turned on concluded that the risk is essentially zero. Those analyses considered both natural and artificial scenarios. They pointed out that cosmic rays, high-energy particles from space, bombard Earth's atmosphere with energies far exceeding the LHC's. If the LHC could create a dangerous black hole, cosmic rays would have already done so billions of times over. The Earth is still here. That is the strongest piece of evidence that the LHC is safe. But it's worth noting that cosmic rays hit stationary particles in the atmosphere, while the LHC smashes particles moving in opposite directions. That difference matters for some exotic hypotheses, but for the black hole scenario, it's not significant. The energy per collision is what counts, and cosmic ray collisions can reach much higher energies than the LHC. So if nature hasn't managed to produce a planet-eating black hole in 4.5 billion years, it's extremely unlikely that we will. However, the fear persists. It's baked into our psychology. We are naturally cautious about technology that we don't fully understand. The LHC represents a level of sophistication that few of us can grasp. It's easy to imagine the worst, but the scientists at CERN are not reckless. They are among the most careful, peer-reviewed, safety-conscious researchers on the planet. They have run exhaustive risk assessments. They have published their findings. And they continue to operate the LHC because the benefits of understanding the universe far outweigh the minuscule theoretical risks. One of the most important lessons from this whole story is that our intuition about black holes is often wrong. We think of them as voracious eaters, but in reality they are just gravity wells. Gravity is weak. A black hole with the mass of a mountain would have an event horizon smaller than a proton. It would have the gravitational pull of a mountain, yes, but that's not enough to suck in the Earth from a distance. You'd have to be very, very close. The idea that a microscopic black hole could somehow grow unstoppably is based on a misunderstanding of how matter falls into black holes. Matter has to lose angular momentum and energy to spiral inward. In a diffuse environment like the Earth's interior, a tiny black hole would hardly ever interact with anything. It's like trying to catch a single specific grain of sand in a hurricane while blindfolded. The odds are astronomically against it. And what about that black hole with no charge? We mentioned it would fall through matter, but if it had an electric charge, it would be repelled by the electromagnetic fields of atoms and would likely get stuck in the floor very quickly. A charged black hole would not sink to the center. It would be pushed and pulled by electromagnetic forces, and it would likely come to rest somewhere in the rock. Still harmless? So even in the most exotic scenarios, we are safe. Now, let's circle back to vacuum decay. Some might argue that we should be more afraid of that than black holes, and in a sense, they're right. Vacuum decay is the ultimate existential threat, but it's also so incredibly unlikely that worrying about it is like worrying about a meteor hitting your house while you're in the basement. The LHC simply doesn't have the energy to trigger it, and even if it did, The conditions required are so specific that the probability is effectively zero. The universe has been around for 13.8 billion years, and as far as we know, no vacuum decay has ever happened. That doesn't mean it can't, but it does mean that if it were easy, it would have already occurred. There is another fascinating angle to all of this: the idea that the LHC could create a black hole that would not evaporate and would not grow, but instead would behave like an exotic particle. This is where we can tie in the cultural reference that many of you might have encountered in Stein's Gate. The characters fear that the LHC will create a black hole, but they also use the concept of the world line and the idea that the future can be changed. While the show takes creative liberties, it does highlight how our deepest scientific endeavors can inspire stories that explore the human condition. The LHC is not just a machine. It's a symbol of our desire to push boundaries, to understand the very fabric of reality. And sometimes that journey comes with a frisson of danger, just enough to make it thrilling. But the truth is, we are not in danger. Not from black holes, not from vacuum decay, not from portals to hell. The LHC is one of the safest scientific instruments ever built. Every time it turns on, the world does not end. And every time it produces a new discovery, we learn something profound about the universe we live in. That is worth the tiny theoretical risk, if you can even call it a risk. In fact, if the LHC ever did create a microscopic black hole, it would be one of the most exciting discoveries in the history of physics. It would confirm the existence of extra dimensions. It would open a new window into quantum gravity. It would validate decades of theoretical work. And then, that black hole would either evaporate instantly or sit there, harmless, and scientists would study it. They would measure its properties. They would learn how gravity behaves at the smallest scales. It would be a triumph, not a tragedy. So the next time you hear someone say that CERN could create a black hole that destroys the world, you can smile and nod and tell them that even if it did, it would be about as dangerous as a falling leaf. The real danger, if any, lies not in the black hole, but in the human imagination, which can conjure up terrifying scenarios that have no basis in physical reality. But that's part of what makes us human. We imagine the worst, we plan for it, and then we go ahead and explore anyway. That's what science is all about. And if you are still worried, just remember, the universe has been throwing particles at itself for billions of years with far more energy than we can muster. If black holes were easy to make, we would already be living inside one. But we're not. We're here, on a beautiful planet, under a star that has another 5 billion years of life left. And in that time, we have the chance to learn, to grow, and to push the boundaries of knowledge as far as they will go. The Large Hadron Collider is our torch in the dark. It illuminates the unknown, and so far, it hasn't burned us. Now, if you'll excuse me, I need to go check if there's a tiny black hole oscillating through my living room. Probably not. But if there is, I'm not too worried. It's just a ghost of a proton, quietly dancing through the atomic emptiness. And I, for one, think that's beautiful. Thank you for watching. But before we close the book on this topic, there is one more cultural touchpoint that perfectly captures the blend of fascination and fear that CERN inspires. If you are an anime fan, you have almost certainly encountered Stein's Gate, a series that revolves around a group of eccentric friends who accidentally invent a microwave that can send text messages back in time. The protagonist, Okabe Rintaro, is a self-proclaimed mad scientist who constantly obsesses over the idea that the Large Hadron Collider might spawn a black hole and end the world. In one memorable scene, he stares at a news report about CERN, referred to in the show as CERN, and rants about the impending apocalypse. The show uses this anxiety as the central plot device, and it resonates because the fear feels real. We watch Okabe's paranoia, and we recognize a little of ourselves in his dread. But what makes Steins Gate brilliant is that it also explores the consequences of meddling with time, not just black holes. The LHC becomes a symbol of unchecked scientific ambition, a gateway to forces we cannot control. In the show, CERN is a shadowy organization that uses particle physics to achieve world domination. It's a dramatization, of course, but it reflects the very human worry that our best tools might become our worst enemies. And yet, the reality is far less sinister. CERN is not a secret cabal. It is an international collaboration of thousands of scientists, all working openly and publishing their results. The LHC is not a doomsday device. It is a microscope, the most powerful one we have ever built. It allows us to see the smallest building blocks of nature, and the discoveries it has made, from the Higgs boson to hints of new physics, have reshaped our understanding of the universe. So, why do we keep coming back to the black hole fear? Why does it persist despite overwhelming evidence to the contrary? Part of it is the sheer drama. A black hole is a cosmic horror. It is the ultimate expression of gravity, a place where everything ends. The idea that we could create one in a laboratory feels like we are playing with forbidden knowledge. It taps into a deep-seated narrative archetype, the scientist who unleashes something they cannot control. From Frankenstein to Oppenheimer, this story is woven into our cultural DNA. CERN is just the latest chapter, but there is another reason the fear lingers. The science is genuinely difficult. Even experts disagree on the details of quantum gravity and extra dimensions. So when CERN itself says there is a non-zero chance of creating a black hole, the public hears, "We might all die." They do not always hear the caveats. They do not hear that the chance is astronomically small, or that even if it happened, it would be harmless. They just hear the word black hole, and their imagination runs wild. I can hardly blame them. I have spent years studying this stuff, and I still feel a twinge of excitement when I think about the LHC. It is a machine that smashes protons at nearly the speed of light. It is science fiction made real. Now, let's bring in that other great fear, vacuum decay. I touched on it earlier, but it deserves a deeper look because it is genuinely one of the most awe-inspiring and terrifying concepts in modern physics. Imagine a universe where the laws of physics are not fixed. They are like a landscape of hills and valleys. We live in a valley that seems stable, but it might not be the lowest one. If we could tunnel into the lowest valley, the true vacuum, everything changes. The particles we are made of would no longer be possible. Protons would dissolve, atoms would break apart. The very structure of matter would be rewritten, and the bubble of true vacuum would expand at the speed of light. You would not see it coming. There would be no warning. One moment, you are reading this. The next, the universe as you know it is gone. It is not a violent explosion. It is a silent, instantaneous reconfiguration. every star, every planet, every living thing would be erased and replaced by something else. Something we cannot even imagine because our physics does not apply there. Before you panic, let me repeat the math. The energy required to trigger vacuum decay is thought to be around the Planck scale, about 10^16 TeV. The LHC operates at 13.6 TeV. That is a gap of 15 orders of magnitude. It is like comparing the energy of a firefly to that of a supernova, but there is a wrinkle. The Higgs boson's mass suggests that our vacuum might be metastable. In simple terms, it means we are living on a knife edge. The universe could, in principle, decay at any moment. But the probability is so low that you are more likely to win the lottery every single week for 1 trillion years. Still, the fact that it is even a possibility makes the black hole fear look almost childish. A black hole is a local event. Vacuum decay is the end of the whole show. So why isn't vacuum decay the headline every time CERN turns on? Because it is harder to dramatize. A black hole is a tangible monster. Vacuum decay is an abstract mathematical ghost. It does not have a maw or an event horizon. It is just a change in the fundamental constants. And yet, if there is one thing that should keep physicists up at night, it is the idea that we might inadvertently nudge the universe into a new state. The good news is that every single cosmic ray collision that has ever happened, and there have been quadrillions, would have had far more energy than anything the LHC can produce. If vacuum decay were that easy, it would have already happened. The universe would not be here. So, we can breathe easy. But it does make for an excellent thought experiment, and it puts the black hole fear into perspective. Now, I want to circle back to a point I made earlier about a charged black hole. Let's paint a picture. Suppose CERN creates a black hole with a net electric charge. That is actually very likely, because the protons being collided have a positive charge, and the resulting black hole would inherit that charge. What happens then? It would not fall through the floor like a ghost. Electromagnetic forces are about 10 to 36 times stronger than gravity at that scale. The black hole would be repelled by the positive charges of atomic nuclei in the ground. It would come to a screeching halt almost immediately. It would essentially be stuck in the concrete, or maybe it would hover just above the floor, unable to penetrate the atomic lattice. And there it would sit, a tiny, charged speck of space-time curvature doing absolutely nothing. It would be like a microscopic dust particle that happens to have an event horizon. You could walk right past it and never know. If you tried to pick it up with a pair of tweezers, you would fail because it is smaller than an atom. The only way to detect it would be to build incredibly sensitive instruments that could sense its gravitational or electromagnetic signature. But even then, it would not pose a threat. It would be a scientific marvel. It would be proof that extra dimensions exist. And then the Nobel Prizes would start rolling in. But here is the kicker. We have not seen any such black holes, not one. The LHC has been running for over a decade. It has produced quadrillions of collisions. If black holes were being created, they would have left a signature. The detectors would have seen a sudden loss of energy and momentum, a particle that disappears into a micro black hole and then evaporates. No such events have been observed. That does not completely rule out the possibility, because if the black holes are very small, their Hawking radiation might be too faint to detect. But it does suggest that if they are being made, they are incredibly rare and Given that cosmic rays have been hitting Earth with higher energies for billions of years, the fact that we are still here is the strongest evidence that microscopic black holes are either not formed or are completely harmless. So, where does that leave us? We have explored the science, the fears, the cultural references. We have looked at black holes, vacuum decay, and the oddities of quantum gravity. We have seen that the LHC is not a doomsday machine. It is a triumph of human ingenuity. It is a testament to our ability to ask big questions and build big machines to answer them. And yes, it carries a tiny theoretical risk. But that risk is so small that it is practically indistinguishable from zero. Every day, you take far greater risks. You drive a car, you eat food, you walk downstairs. All of these activities have a non-zero chance of killing you. The LHC has a non-zero chance of creating a black hole that does absolutely nothing. I know which one I am less worried about. And yet, the fear will not go away. It is part of being human. We are wired to imagine worst-case scenarios. It is a survival instinct. But we also have the ability to reason, to examine the evidence, and to understand the odds. When we do that, we find that CERN is safe, the universe is safe, and the pursuit of knowledge is worth the tiny theoretical gamble. In the end, the story of CERN and black holes is a story about perspective. It is about how our imagination can outrun reality. It is about the line between science fiction and science fact. And it is about the bravery of scientists who dare to push boundaries even when the public is afraid. They do not do it because they are reckless. They do it because they understand the risks, and they know that the rewards, a deeper understanding of the cosmos, are immeasurable. So, if you ever hear someone say that CERN could destroy the world, you can smile and offer them a different perspective. You can tell them that yes, the LHC could create a black hole, but that black hole would be the most harmless thing you have ever seen. It would be a scientific wonder, not a world ender. And if you want to be truly terrified, look up vacuum decay. But even then, take a deep breath. The odds are on our side. Now, I am going to leave you with one final thought. Imagine for a moment that the LHC did create a microscopic black hole. Imagine it survived with no charge and somehow avoided all interactions as it passed through the Earth. Imagine it settled at the center of our planet, a tiny point of infinite density. What would happen? Nothing. It would just sit there. It would take billions of years to eat even a gram of matter. Long before it became a threat, the sun would expand and swallow the Earth. And long before that, humanity would have evolved, or gone extinct, or traveled to the stars. The black hole would be a silent witness to our story, a ghost in the machine of the Earth. And one day, when the planet is gone, it would still be there, drifting through space, a tiny relic of a civilization that dared to reach for the stars. That, to me, is not terrifying. It is beautiful. It is a reminder that even the most extreme objects in the universe are subject to the laws of physics. They are not monsters. They are not gods. They are just consequences of the equations that govern our reality. And we, armed with those equations, can understand them, predict them, and even create them in a controlled environment. That is the power of science. So, thank you for joining me on this journey. I hope you now have a clearer picture of what the LHC can and cannot do. I hope you are less afraid and more curious. And I hope you will continue to ask the big questions, because that is what makes us human. We ask, we explore, we learn, And sometimes we even create little black holes, but we never let them win. Until next time, stay curious. And if you feel a tiny tremor beneath your feet, do not panic. It is probably just a proton, dreaming of becoming a singularity.